All right, so hello everyone, and welcome to another show of Echo Live. Thank you so much for joining me here today. My name is Sierra, and I am an astronomer here at the Michigan Science Center. So as you guys are now entering the room, go ahead, introduce yourselves in the chat. That's mainly how we'll be talking back and forth to each other during this program. And while you guys are putting in your names and where you're from, I want you guys to consider a question, okay? So I said that I'm an astronomer. Now, does anyone here know when astronomer studies? Any guesses? If you do, go ahead and put your guess in the chat. I will give you a hint. So today's program is called Ice Worlds. Now, astronomers don't necessarily study ice, they sometimes do, but they definitely study worlds. Any guesses so far? What do you guys think? So astronomers actually study planets. And not only planets, but they study stars, they study moons, they study basically anything you can see when you look up at the night sky. So that's what I study. And today we are actually going to be looking at some ice worlds of our own. Now, before we go visit some of the ice worlds in the far reaches of our solar system, we're going to start a lot more locally. We're actually going to start on our very own ice world, which is the Earth. So let's take a look at some of the ice that we can find right here on planet Earth. All right, so the Earth is actually covered in two major ice sheets. Now, ice sheets are basically a large mass of glacial land ice that is larger than about 20,000 square miles. Like I said, the Earth has two major ones covering Greenland and the Antarctic. Now, together, these two ice sheets combined make up over 99% of all of the freshwater ice on the planet. That's a lot of ice. In fact, the Antarctic ice sheets, when combined, is over the size of the United States and Mexico combined. So very, very large. Now, ice sheets can only form in places that are very, very cold, like our two polar ice caps. That's because they need to form in an area where it's not too hot in the summer. So all of the snow that falls during the winter months then don't get melted off during the summer. So that's why they form at our two polar ice caps where it's very, very cold. How these ice sheets work is that the new snow falls in and lands on top of the old snow, pushes it down, and basically compresses it until it becomes this large ice sheets. They take a very, very long time to form, thousands and thousands of years. So that's why we only have these two major ones here on the Earth. So now we know where we find all of our ice here on the planet. But how do scientists study them in the first place? Well, scientists actually use something called an ice core. So scientists take ice cores from the two polar ice caps or from ice sheets, and then they study them to learn about changes in the Earth's climate. Now, the oldest ice cores, which you can find in about East Antarctic, provide an 800,000-year-old record of the Earth's climate. Each season's snowfall has slightly different chemical properties, and because of that, we can see the differences in the climate from year to year. As you can actually see in this image, each new snow layer has slightly different properties than the one before it. Because of that, it creates these visible bands that we can see in the ice core, kind of like the rings that you would find on a tree. However, the more that ice compacts and the less snow that accumulates, it gets harder to see these annual layers. So in order to analyze these deepest layers, scientists use a whole lot of different methods. These include measuring the chemical composition, measuring the electrical conductivity of the ice, and scientists can also use computer modeling techniques that can help to understand the relationship between the depth of the ice core and the age of the ice. Now, in this picture that we can see right now is an ice car from the West Antarctica. In this image, we can actually see the layers of the dark bands right over here. And these dark bands were actually made by volcanic ash that settled on the ice sheet about 21,000 years ago. So the deepest ice core records come from the Antarctic and Greenland, where the very deepest ice cores can get over 2 miles deep. Now, in front of me, I actually have an example of an ice core that you guys can make at home. So let's see, let's take a closer look at my very own personal ice core. All right, so as you can see, this one I actually made in our very own lab here at the Science Center. Okay, so as we can see, Right now, it is made up of distinct bands. So these distinct bands form the different layers that we can see. I'm going to turn off my virtual background. There we go. So you can see those bands a little bit clearer now. Okay, fantastic. So how I made this and how you guys can actually make it at home is to freeze liquid in different layers. So this first one that I froze, I added some water into a clear plastic container, and then I added some food coloring. So I added green for this layer. And then after it froze, I added another layer. So this one I made a dark pink color. I really like the color pink and I like red as well. That's why my hair is red. But as you can see, I added something a little bit extra in it. So it's not just colorful. So these things are representative of the different things that scientists might find in an ice core. For example, this very, very top layer, this blue layer here, you might be able to see in this image, but there are some sparkling aspects. You can definitely see this bright one right here. So these little sparkles that we can see actually represent tritium. So this is a radioactive isotope of hydrogen. So when scientists find these radioactive isotopes inside of ice cores, that means that during the time of forming, there was a lot of radioactive elements in the air. So we can actually tell the radioactivity of the atmosphere at the time of the snow forming. So we've learned a lot actually from being able to study that. In fact, ice core records can actually be dated to the Chernobyl disaster in 1986. So we can see records of that in the ice themselves. Some other things that we can see here is that, for example, when we're measuring the chemical makeup of the different ice, some elements take a lot colder temperatures in order to be able to be condensed down into ice. For example, over here, we have two different sized beads. We have these small black beads and then some bigger green beads. These represent the isotopes of oxygen. So there are two major isotopes of oxygen that we can see in ice. We can see oxygen 16, oxygen 18. Oxygen 16 is a lot lighter than oxygen 18. So if we find it in the snow, that means that it was very, very cold at the time the ice was forming. So we can actually tell the different temperatures of the ice just by studying the ice core. So that's how we're able to learn about the Earth's climate by studying the ice. All right, so now we know how we study ice here on Earth's surface. But I think it's about time for us to get into our imaginary rocket ship and actually go visit a couple other planets. So I want everyone to strap into their imaginary rocket ship. You have to put your seatbelt on. So let me hear those clicks, click, click. Okay, since we're all strapped in, now we're going to leave our planet behind and we are going to go far out into the outer reaches of our solar system. Now, you guys are probably a little bit familiar with what we're going to visit next, because there are a couple of the planets that we can actually see in the night sky. So without further ado, let me reintroduce you guys to our next ice worlds, which are Uranus and Neptune. So Uranus and Neptune are both gas giants. In fact, the four planets that make up the outer rings of our solar system, which are Jupiter, Saturn, Uranus, and Neptune, are all gas giants. But Uranus and Neptune are a special type of gas giants. They're called ice giants. They got that name because they have a slightly different chemical composition than Jupiter or Saturn. That's because they are much further away from the sun than Jupiter and Saturn are. So that means that they formed in much colder conditions. Because it's so much colder where they are, heavier isotopes can actually become ice. So it's cold enough for them to compress down into ice, into their solid form. All right, so on Earth, when we're talking about ice, we generally talk about like water ice. You guys have probably heard of dry ice before. That's carbon dioxide ice. But in the outer reaches of our solar system, it's actually cold enough for a lot more elements to form ice. So in something like Uranus or Neptune, we might find methane ice, ammonium ice, hydrogen sulfide ice, or even phosphine ice. So they can all freeze out there in the outer reaches of our solar system. Actually, the visible clouds that you can see right here on Neptune's surface are likely made up of different ice crystals of the different elements that we just talked about. Now, other than Uranus and Neptune, there are other examples of icy worlds right in our solar backyard. For example, you guys are probably familiar with the dwarf planet Pluto. So in the area past Neptune is called the Kuiper Belt. And that's where a lot of very, very, very cold objects are located in our solar system. That includes the dwarf planet Pluto, also the dwarf planet Eris, and a bunch of other things inside of our Kuiper belt that are mostly made up out of ice. What else is made out of ice in our solar system? There's also comets. So comets, you can see, they're big, big chunks of ice that when they get close enough to the sun, it forms this long, bright tail coming out the other end of it. That's that really, really cold ice getting melted by the sun's presence. And another thing that is made up of ice in our solar system are moons. So while we may only have the one moons, other planets in our solar system actually have a lot more. In fact, let's think about some other moons that we can find. Well, Triton, which is the largest moon of Neptune, is mostly made out of ice. Enceladus, which is the sixth largest moon of Saturn, also made up of a lot of ice. In fact, there are a lot of icy worlds in our solar system that actually are made up of moons. And in fact, that brings me to one particular moon that I want to talk to you guys about. And that moon is called Europa. So Europa is very, very important moon to astronomers. And I'll talk a little bit about why that is. So Europa is the smallest of the 4 Galilean moons. What that means is that Galileo himself helped discover these 4 moons that all orbit Jupiter. Now, Europa is the smallest of them, but there's a lot of other interesting qualities about it. For example, Europa is believed to have a mostly water ice surface, with this icy shell about 10 to 15 miles deep, so we believe. So everything we're seeing right now in this image is actually made up out of ice. And these cracks that we can see are cracks that is formed in these icy shell. So we talked a little bit about the ice, but what's really interesting about Europa is that we actually believe that underneath this icy shell is a liquid water ocean. This ocean might be as much as 100 miles deep. What that means is that even though Europa is about 1/4 the size of the Earth, it may contain twice as much of all of Earth's oceans combined. All right, so now we know that we have liquid water somewhere in our solar system, or at least we can guess. But how do scientists know that in the first place? How do we know that there's an ocean underneath Europa's icy shell? It's definitely not something we can see just by looking at this image, right? Well, actually, we were able to observe evidence of liquid water. So let's actually bring up that evidence. So both the Hubble Space Telescope and the Galileo spacecraft have seen evidence of plumes of water being ejected from about 100 miles above Europa's surface. If these plumes do exist, theoretically, a spacecraft could actually travel through these plumes and figure out the chemical composition of the water inside of them. So why is that useful? Well, it's a possibility that there may be microbial life form inside of Europa. So when we talk about finding different types of life form in our solar system, Europa is a very, very good candidate. It has liquid water, which is one of the things that we've identified as being core to the idea of life. All right, so pictured here is actually a picture of Enceladus, another one of those icy moons that we talked about earlier, where we've also been able to absorb, or I should say, observe these different plumes that we can see from its surface. All right, so how are these plumes being ejected into the atmosphere, into the space around it? Well, to be honest, we're not entirely sure, but we do have a pretty good guess, and we called it the cold geyser model. So how this works is that there is tidal heating happening inside the core of Europa and Enceladus. So tidal heating is basically when the gravitational pull of Jupiter is pulling on the core of Europa and Enceladus and causing that core to flex. So that's how it's able to be hot inside the cores of these moons, even though they're very, very far away from the sun. So this tidal heating is creating that warmth. And when that warmth comes in contact with that pressurized liquid water that's a lot colder, it is actually vented and ejected to the surface of the planet. Now, what might that look like? Actually, I have another demo here which may demonstrate what these cold geyser models might look like. And in order to do that, I am going to use something called liquid nitrogen. Now, liquid nitrogen is very, very cold, so it's not actually safe to use at home. Luckily, you guys don't have to worry about trying to do it out of your home because you can see it right here in our studio today. So let me zoom out just a little bit so you guys can see what I have here a little bit easier. All right, so in front of me right now, I have a jug of warm water. So this is the sort of water bottle that you might see at school or at the office. At the very, very base, I have some warm water. Now, in this container, I have my liquid nitrogen. And liquid nitrogen is very, very cold. In fact, it's about 321 degrees below freezing. So because of that, it's not very safe to use. So whenever I use my liquid nitrogen, I make sure that I have my proper safety equipment. So that's why right now I'm actually wearing this lab coat and I'm going to put on these gloves. All right, so when my liquid nitrogen is introduced to my hot water, we are going to see something happen very, very quickly. You guys might be familiar with what happens to liquids when it gets warm. If we're familiar with our states of matter, it forms a cloud. This is called condensation. So let's pay very close, careful attention and see what happens when I add my liquid nitrogen to my warm water. All right, so as you guys saw, we were able to create a geyser. So this is really similar to something that we might be able to see ejecting out the surface of Europa or Enceladus. Let's see if I get a little bit more coming out. All right, I think that's as much cloud as I can create right now. So all of that pressurized air is being forced out of a much, much smaller container, and that's what's causing that ejection to happen. And we can see something very, very similar happening to our ice worlds. Now, what does this have to do with, let's say, being able to find life on these other worlds? Like, so we have water, so we have some heat. It seems like there's a lot of other things missing that we would need in order to have life in the first place. Well, actually, we think that these vents might be another clue as to how we might be able to find life on these icy worlds. So let me bring up a picture of something that we actually have here on Earth. So this is an image of a hydrothermal vent, and it's found on the ocean floor. So when we have these tidal heating, it's possible that this hot burst of air is able to burst out from the core of the planet itself. When this happens, it might be able to create the necessary building blocks for life in the first place. So that's where a lot of our deep sea animals here on the surface of the Earth is able to find the chemical building blocks for life. And that's how places like Europa or Enceladus and other icy worlds might be able to have life inside of the planet. All right, so if you're interested in learning more about Europa, actually in 2024, NASA is launching the Europa Clipper mission, and its job will be to figure out if Europa is actually capable of potentially hosting life. All right, so this does actually bring us to the end of our program today. Thank you guys so much for joining me here today. I had so much fun talking about icy worlds with you all. And if you want to join us next week, we'll be at the same time. We're always Wednesdays at 2:30 p.m. Eastern Time. So thank you guys so much for joining me. I had a lot of fun, and I'll see you guys very, very shortly. So bye, guys.